worksheet I just returned, the Vesper worksheet.
Okay.
I want to work through this. We'll also use this to review polarity. So if you didn't turn it in, that's a problem. But you should probably pull it out. This way.
That's the one that you just handed back.
This is the one I just handed back. You have it, Gavin. I just don't know where it is. So, somehow a lot of people manage to just forget number 1. But you kind of need to answer all the questions on a homework assignment. Remember, this has to do with the lone pairs and the bonds all repelling each other, and they try to get as far from each other as possible.
This one?
No, the one that says VSEPR worksheet.
The one that she literally just handed back.
He didn't turn it in.
Oh.
Oh, right. The most common mistake I saw was confusion between trigonal planar and trigonal pyramidal. So, number 2, I'm just going to give you these answers really quickly. The boron triiodide, this is an exception to the octet rule. Because there are 3 bonds but no lone pairs, this is trigonal planar. So we're going to be flat and the bonds be what? About 120 degrees. Okay? That is because there are no extra lone pairs. And you can't just stick lone pairs in there because you don't have enough bonding pairs. Okay? 3, I think we know 3 backwards and forwards. CH4 looks like that. What's its shape? Tetrahedral. No, because NF3, this one, you might set it up like this, and then you realize, oh no, I have another bonding pair. You can't turn something into a double bond to make fluorine happy, sorry, nitrogen happy. You just put it there. Yes.
Where did shapes come
Section 8.4, and if you, we might need to meet and go over that individually if you're confused. If not, start with reading the textbook. Start with the textbook, start with the worksheets. I will go from there. Caleb.
So, I would have either erased one pair on one fluorines, and then I made a line in between N and L. Would that still be?
Nope.
Oh,
Because
and I didn't.
if
I didn't
F
use
tries
the
to double
dots.
bond like that, now nitrogen has too many.
Well, I didn't use the dots.
Then you have too few
Oh, yeah.
bonding pairs. So, because this has 3 bonds and a lone pair, what shape is it? Trigonal pyramidal. It has an extra lone pair. It's a pyramid now. Let's look at SiF4. You might recognize it as being almost the same shape as methane, right? You have this thing that wants to make 4 bonds in the center, and you have something that wants to make 1 bond all around. And so what shape is this?
Tetrahedral.
Tetrahedral. For number 6, remember I said to change to NCl3, not NCl4. So, you might recognize this as being the same shape as NF3. You start to recognize these same shapes coming up. Things in the same groups act the same. So, we have our central atom, and if you add up the bonding pairs, you realize, oh, it's also going to have a lone pair. What shape is this?
Trigonal pyramidal.
Trigonal pyramidal. CS2. Let's work through the whole process of this one because it's trickier and it's good review. Remember, we start with estimating positions. We can guess it's going to look something like this. Let's not put bonds in yet. Now we add up our valence electrons. We've got 4 from the carbon. We've got 6 from each sulfur. So in total we have 16 electrons. And how many bonding pairs do we have? 8. And we start filling them in. 1, 2. Then our next step is we fill in the terminal atoms. Sit up straight, Gabe. 3, 4, 5, 6, 7, 8. So we have all our bonding pairs put down now, but our next step is going to need to be make the carbon happy. So we need to make both these sulfurs stay happy, but also make the carbon happy. How are we going to do that, Adeline?
You do the,
Gavin?
you take the 2 off the top, and then you add it, and you share it
You
with carbon.
turn one of sulfur's lone pairs into a bond.
On both sides.
Isn't that what you said?
And then you do the same, no, she just said put a bond there. Doesn't matter if you, Jack, unnecessary. Doesn't matter if you know the answer, it's about how you write the answer and communicate the answer. So,
What I wrote, so you didn't mark it wrong.
well, you got lucky.
I just did, instead of doing bonding pairs, you just,
No?
I just had this.
Well, I was mostly looking at the identification of the shape. Because what shape is this? 2 bonds, no lone pairs makes this linear, not bent, because there's no lone pairs on the carbon. Okay, next page we have NH4 plus 1. This one, we've made it before, so we won't go through it. Should end up looking like this. You have to notate that this is an ion. And what shape is this going to be? Good, let's look at SF2. In fact, this is basically the same shape as, what was the other one I was thinking? H2O. Because S is in the same group as O, and F can make one bond just like H can. Alright, we guess the position. And you may be thinking, oh, this will look like CS2, right? I don't know, but you add up the bonds. We've got 6 valence electrons from sulfur. Each fluorine is bringing 7 with it. How many?
26.
Oh no, 20. So we've got how many bonding pairs? 10. And we start placing them 1, 2, 3, 4, 5, 6, 7, 8.
Boom.
We have 2 more.
9, 10.
We're not going to worry about double bonds. We can put them here and here. Now, if you put them like this, it's really tempting to say that's linear.
But it ain't.
But we're not going by what the Lewis structure looks like. We're going by those tables of molecular shape. And did I give you this chart?
Why can't you
No,
double,
you did not.
why
But I have
can't
it right
you do
here.
the
I've
double
been
bond
using
in the
It has no need for a double bond. Double bonds are only when electrons actually need to be shared. With all your 10 bonding pairs, you can make everyone happy without having any double bonds. And if you try to make a double bond, either the sulfur or the fluorines would end up with too many electrons. So this turns out to be bent because in reality, both of those lone pairs are working like here and here, here and here, and then you have the other fluorine coming off here.
Oh.
Oh yeah. Remember like a water molecule? Alright, xenon tetrafluoride. We went over this one, but let's go over it again. This is a weird one, so let's work through the whole thing again. We can guess the shape, right? And you may be really tempted to just call it tetrahedral and be done, but you don't skip the inside steps.
Yeah.
How many valence electrons does xenon provide?
Good to know.
8. How many does each fluorine provide? 7. So how many valence electrons total do we have? 28 plus 8, which is 36, which is a lot. So start filling them in. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Where on earth are those last two going?
I'm using.
And then you're gonna say, well, Xenon's weird. Good. Remember, this one is not in your book. On the test, you will not need to know any of the molecular shapes that aren't in the book. But this is why I gave you that extra molecular geometry sheet. If we have 4 bonds and 2 lone pairs, what do we call that shape? Square planar. It's actually going to be, the fluorines are going to be 90 degrees apart like that. And you'd have, if this was 3-dimensional, 1 lone pair here and 1 lone pair behind the board. Alright, let's look at Bro. BRO3.
Bromine oxide.
No.
Or bromide.
No.
Boron oxide.
No, it's not.
It's boron.
Notice it's an ion. What is the name of this ion?
My bad.
Bromide.
Is it bromite or bromate?
Bromate.
It's not going to be bromine trioxide. It's an ion.
Bromate.
It says it's an ion because it has a little minus charge. BRO3 would be bromine trioxide. BRO3 minus
Bromate.
is bromate.
So bromate.
So we guess our positions. And we count up our electrons. How many from the bromine? 7. We get 6 from each oxygen, and it's a negative ion. It's an
Minus one.
anion. So we get to add an extra
So
electron.
it's 24. Or 26.
Correct. 18.
18 plus 8 is 26.
Yes.
We've got 26 electrons. How many bonding pairs?
14.
4.
No, 13. 13. Can it be messed
13. We know how to count.
And you mentioned
I promise you.
bandwagon.
3, 4.
We're up to 12. Where should 13 go?
Right on bromine.
Is this done?
No, yes.
No.
No?
Just
You
saying.
need that build the bobbers.
I got bobbers.
It's a triangle.
Brackets.
What close?
What shape is this?
Triangle pyramid.
Trigonal pyramidal.
Yeah, triangle pyramidal. The broad pyramid.
Those electrons force it into being a 3-dimensional shape. It forces it into being pyramid shaped instead of a plane shape.
I split the wrong answer.
Triangle pyramid.
Okay, Jack, you do not need to make up for a week's worth of words you didn't say in class.
I'm sorry.
Then fix it. Alright, now, let's think about polarity. Yay! Starting with something like, how about CS2? Because now we know the shape for that, right? I need to redraw it, but that's okay. Remember when we talked about polarity, we had to distinguish between polar bonds and polar molecules. How do we know if a bond is polar? Raise your hand.
What was the question?
How do we know if a bond is polar?
Is that equal? It's not equal.
Equal in what? So which answer? Those are 2 different answers. Electronegativity?
That's what
You need difference in electronegativity. Sit up straight, Gabe.
Oh, yeah.
it's like.
Gavin? No. Focus. Now, our carbon, you can just assume that any nonmetals that are not identical are going to have an imbalance of sharing electrons. They're going to have difference in electronegativity and be making a polar bond. Feet on the floor, Gabe. So, is it going to be a polar bond between carbon and sulfur? Are they different elements? Yeah, so they have different electronegativity. If you need specific electronegativities, I will provide you with a table of those. Okay? Who is going to be pulling on the electrons more, oxygen or sulfur?
Sulfur.
Oxygen? What?
What oxygen?
Yes.
That's carbon.
Sorry, carbon or sulfur?
Carbon. No sulfur.
So that one you can't just guess from the periodic table. You'd have to look at the numbers in your textbook or on the table that you're going to get. Carbon has an electronegativity of 2.55. Sulfur is 2.58. Sulfur is pulling a little bit more on the electron. That's really close. But that does make each sulfur a little tiny bit negative. However, is this a polar molecule?
No.
To be a polar molecule, you gotta have one area of the molecule that is more positive or more negative than the other area. One side. So think of this as just a shape like this. This side's a little bit negative, this side's a little bit negative. Does it have a plus and a minus pole?
No. So it's not polar, but
It's a non-polar molecule that has polar bonds.
Okay.
Let's do more of these, because it's really good to practice finding those polarities. We went over the whole study guide, didn't we? Yes, I think we did. So this is just, I think, the thing that you are probably going to be wanting most review on, because everything else we've been going over for so long. Yes?
Very good, Rich.
Yes.
Use that sheet you gave us at like the end of class when you did.
So that we probably won't go over, it won't be turned in, but you can use it as review. We're using the worksheet I just returned to go over polarity stuff. Let's look at something like NF3. Which we know is shaped like this, right? And it's actually forming that little, I can't quite draw it, it's like a three-dimensional shape like so, where you have this lone pair sticking out on one side.
The triangle pyramid.
Yeah. Trigonal pyramidal. Is the bond between nitrogen and fluorine polar?
Yes.
Who's pulling on the electrons more?
Fluorine.
So who's going to be a little bit minus? A little bit negatively charged?
Fluorine.
Fluorine is hogging the electrons more,
All the fluorine.
so it's getting a little bit negative.
Those eights.
Those are lowercase deltas to mean partially. Partially negative. I would probably not give you a problem this difficult, because you have to kind of look at this and say, oh, which is, you're saying, if we look at this three-dimensional version, all of these are a little bit negative, but this is also 2 electrons over here, right? This is very negative. This molecule is probably partially polar, but not much. Do you see why?
Is it more non-polar then?
Right. It's leaning more towards being non-polar.
Okay.
Let's look at something that is a little bit more definite. How about? Like, like what? I haven't decided.
What's happening?
Hmm?
What's happening right now?
I'm choosing a sample problem
Oh.
to inflict upon y'all. I mean, to review, to go over. It'll be fun. I lost the sheet I had given y'all. The somebody have that, oh, no, maybe, here, found it. How about COF2? This looks like a fun one to figure out the Lewis structure for, right? Who do you think is going to be in the center, C, O, or F?
C.
C, least electronegative. So I guess that it's probably going to be something like this. We counted our valence electrons. Hopefully this is something you're comfortable with.
24.
How many bonding pairs?
Whoa.
1, 2, 3. Now we start filling in. 4, 5, 6, 7, 8, 9, 10, 11, 12. For reasons that are beyond the scope of this course, oxygen is more likely to form the double bond. For the purposes of the test, there may be some problems in which you're given a formula as to find the Lewis structure, the molecular shape, and identify whether the molecule is polar. There may also be some where I show you the Lewis structure and ask you to identify if it's polar or not. I would not expect you to figure out this Lewis structure on your own because I wouldn't expect you to know that oxygen is more likely to make the double bond. But I would expect you to be able to figure out, is this polar or not? Okay?
Is that tomorrow?
Yep. I'll post this recording online if that would be useful for people. If you want to review the whole class again.